When we looked at adding nodes to the tree, it should be somewhat clear that it's really not that difficult to insert data into the tree. So it might surprise you that remove is actually quite complex. In fact, it's probably the most complex algorithm we'll look at in this entire course. So remove has three distinct phases. First, you find the node to be deleted. If the node does not exist, we exit. Now remember from find that it's easy to tell if a node does or doesn't exist in a tree, and it's pretty efficient to do that. Now, if the node that we found is a terminal node or it's a leaf node, you simply remove it from the tree by nulling out the parent's pointer to the node we're deleting. Now, a key point here is when we find that node, we need to know its parent. In the examples we'll be looking at, our trees are not storing bidirectional links. So we're going to need to keep track of not only the node we're deleting, but its parent. And for a non-leaf node, what we need to do is find the correct child to replace the node we're deleting. And this is actually a little bit of a tough concept to grasp without showing some pictures, so we're going to move on to that pretty quickly. But I want to let you know up front, there's three different scenarios, so this is quite in depth, and I would encourage you to watch this a few times if you feel like you're not getting it, because this is really important to get right, and it's one of the most difficult parts of a binary tree. The first case we're going to look at is where we're removing a node that has no right child. So if you look in the tree, there are several nodes here that have no children to the right. The 8 node has no right child, and the 1, 3, 5, and 7 nodes have no right child. So this case would apply to the removal of any of those nodes. We're going to look at the removal of 8 because it's the most interesting case. So the first thing we do is we find the node to remove. The 4 is not it, 8 is larger, so we end up on the 8 node. Now the 8 node has no right child, so what we're going to do is promote its left child into its place. Now I want you to think about why that's the case. Since there's no child to the right, there is no value underneath the 4 that is going to be larger than 8. So when we perform the delete operation, we've now promoted that tree, the 6, 5, 7 nodes, up in place where the 8 was. And this works because we haven't broken the invariant structure of the tree. Everything to the right of the root node is greater than the root node. And when you go down to the 6 node, everything to its right is greater than 6, everything to its left is less than 6. So we've been able to retain the rules that the tree must follow while only having to move one block of nodes around. So now let's look at the next case. In this case, the node we're removing has a right child that has no left child. That's a mouthful. So look at what I mean here. Let's say we're removing the node 6. The node 6 has a right child, 7, that has no left child. So what's going to happen in that case is the right child will replace the remove node. Let's take a look at that. So we're removing 6. We have to find the node first. It's greater than 4, so we end up on the 6 node. The node to the right has no left child. The 7 has no left, so we're going to promote that right child, the 7 node, up to where the 6 node is. And now this is going to mean not just repointing 4 to 7, but 7 also has to become the parent of 5. So what we did there was we moved that entire right tree up into the remove node slot. And again, this works because we haven't broken the invariant structure of the tree. We know that everything to the right of 7 is going to be greater than 7, and everything to the left will be less than 7. So let's look at the third case. The node we're removing has a right child that has a left child. So on this tree, that would be the node 6 again. The 6 node has a right child 8 that has a left child 7. And what we're going to do is the right child's leftmost child node will replace the removed node. So let's look at that. We're going to remove 6. First we find the node to remove. It's greater than 4, so we go to the right and we found 6. The node on the right has a left. So what we do is we find the right child's leftmost child. So the right child is the 8, and its leftmost child is 7. And then what we do is we promote that node into the deleted slot. So we're going to take 7 and move it up to where the 6 node was. And now notice we've retained the invariant structure. Everything greater than 7 is to the right, everything less than 7 is to the left. And the reason we use the leftmost child is because we know the leftmost child is going to be the smallest value in the tree. So what we've looked at here is the 3 different remove cases. Remove is complex. There's a lot going on, and it's hard to explain it all, even visually. So I really encourage you to watch this clip over again if you're feeling like you don't fully understand it. And I would really encourage you to actually draw some trees out and think about what it would mean to delete some data, just like we did here on the screen. And we ran through some deletion scenarios. Go ahead and do some more of those. And start to come up with other scenarios, like what if the leftmost child in this case had children on the right? What should that tree look like? As long as the tree you come out with follows the invariant rules of a binary search tree, you're coming out okay. And you're not going to be able to do that unless you follow all the rules. So this is a great way to really reinforce some of these things and help you understand it.